So we have already seen how the non-local means filter works. Now I'll show you some of these examples, which will try to illustrate how well this filter works as compared to your averaging kind of filters, which are all very local. Right? They all do local averaging, including your mean filter, the Gaussian filter, and so on. Now, some of these slides are self-explanatory because we've gone through them already. But in any case, I'm going to go through each one of them. So if you see. So a mean filter, okay, we've already seen these equations. It's like a box filter, has all uniform weights, okay, and then the kind of filter, right, that you get out of this is actually is what I would say spatially invariant because of the fact that the weights remain the same irrespective of where you are in the image, right? Irrespective of which location you have chosen, the weights remain the same. The Gaussian also is very similar, just that the weighting is not uniform, but otherwise it is also a spatially invariant filter. Wherever you go, you will get the same set of weights, and therefore both mean as well as the Gaussian filter can be implemented using Fourier transform because convolution holds. But then the issue, of course, here is a Gaussian filter. You can see that they see the shape of this filter. It has a maximum in the middle. The weight is maximum in the middle, and then because it tapers off as you go outside. And then right here is an image. So that is a pixel, right, that you're looking at that has been shown in red dot, and then you're trying to filter it. Of course, your filter size will typically not be as big as what is being shown in this image. It's only an illustrative picture. But it will be like 6 sigma plus 1 cross 6 sigma plus 1, which may be 13 or 15 or something. Right? Typically, it's not bigger than that normally. But then the point is, whenever you use a mean or this Gaussian filter, you will end up with weights that are constant. But then this also causes something like a space invariant blur because any averaging operation will introduce some amount of blur. And because it's weighted averaging or uniform averaging is constant across the entire image, so it causes what we call a space invariant blur. This is bad for applications such as denoising because of the fact that it cannot retain the edges, right? For the reasons that we've already seen before. Then denoising additive. Okay, now I'll skip this non-local means filter. I've already explained to you how this works, and we'll just see as to what kind of output you get. Now, for example, here is a noisy image. Okay, this is a noisy input image. This is another noisy input image. And then when you actually input it through the filters, if you look at the mean filter, the output looks very smeared. The vertical edges are all blurred out, right? Similarly, for example, even look at this horizontal edge, which is supposed to be sharp here. In the noisy image, it is sharp, but then here it's all blurred out. So the Gaussian filter may be a shade better than this, but then it also is not anything spectacular. Whereas a non-local means filter is considerably better, right, than both. You can see that the edges are well preserved. They are not smeared out. Even the horizontal edges are very good. Even this small little blob that you see here that has gotten certainly smeared in the other two, right? It looks quite sharp in the output image. Now, as you would expect, right? You can another way to interpret this non-local means filter is to sort of look at this patch with this P, okay, which has been taken on the edge, and now suppose we try to see what weight will Q1 get and what weight will Q2 get and what weight will Q3 get. Then by looking at this image, it is obvious that Q1 and Q2 should get a higher weight as compared to Q3 because Q1 and Q2, the patch around Q1 and Q2 look very similar to that around P, whereas the one at Q3, right, it looks like something else. Okay, and therefore, look at this, what exactly happens. If you traverse on this hat and if you try to see what kind of weights you get for this pixel at P, then you see that over the entire image, it's only over the hat that you get the weights that are significant. Everywhere else, the weights are almost zero. Similarly, if you were to take this pixel right out here on this edge, then you see that the weights that you get for all the patches from around from this entire image, what you find is that you get only significant intensities right along these two lines, okay, which are also similar looking edges, whereas elsewhere, right, those weights are very weak. Furthermore, right, you can kind of go to, let's say, one more case. One more situation. Okay, here is Lena that has been filtered. Now, Yaroslavsky filter is a filter that works very similar to NLM, except that it looks at individual intensities. It doesn't look at patches. And therefore, you see that the Gaussian filter does not do a good job. The Yaroslavsky filter gives you an output that you can say is better than the Gaussian output, but nothing great. Whereas the NLM filter looks really, really good, right? So to be able to come from there to this is really appreciable, right? And then you can see a few more examples where we have kind of shown you the weights. So, for example, if you look at this is a texture image, which is kind of a brick wall. You can see that if you take a P that is at the intersection of these three lines, then all your weights come from similar locations. right? It's very, it's a kind of a distinct thing that stands up. Whereas if you took a patch, right, around which there is no great structure, then you see that the weights get smeared out, right? So something like this is not really very nice, but something like this is excellent. Okay. So all these examples serve to illustrate that NLM clearly beats other filters hands down, especially these local averaging filters. And of course, there have been further improvements over NLM. There is something called a BM3D filter, which is actually block, which is called block matching and the 3D filtering, which is kind of a collaborative filtering. That is the most recent one, which came out in 2007. Okay, that is by Alejandro Foy, and that is again another filter which, if you are interested, you can actually go through. Okay, it uses it uses a unitary transform kind of an approach in order to be able to. It is also patch based, right? And then, right, it uses some other kind of unitary transform filtering in order to be able to reduce the effect of noise. For those of you who are interested, you can actually read the BM3D. Also, now that you have all this background, it should be fairly straightforward for you to follow BM3D.